So one of the things we'll focus on as we're finishing up with our Gauss's law problems is what happens when you put a conductor into an electric field. So up till now we've been focusing on Gaussian surfaces within an electric field, and we said because those aren't real surfaces they don't change the electric field. But what we'll see here is that when you put a conductor within an electric field, it actually will make changes to the electric field. So what happens? So when we put this conductor into an electric field, because it's a conductor, that means it has free charges. And so those charges move in response to the field. And so here we have a constant electric field that points downward. That would be as if there was a positive plate up here at the top, a negative plate down here at the bottom. And so the charges, the free charges on our conductor are going to move so that the electrons will line up over here. That will leave a deficit of electrons along this side over here. And basically the charges will continue to move until the field that they generate. So you notice if we go back one, you'll see that there's an electric field. So the purple is sort of the external electric field, but there's the yellow vectors are showing an electric field that's being generated inside the conductor itself. And so you notice basically what's happening is that the charges are realigning along the surface of the conductor to generate an electric field, and that electric field just happens to cancel out the electric field inside the conductor. So what that means is you have a net external field that points downwards, but the charges have rearranged themselves to create an electric field that points upwards that just cancels out the electric field inside the conductor. So that means that the electric field inside the conductor is zero. Right? There's no electric field inside the conductor when it's in electrostatic equilibrium. Now, what will happen is usually you put a conductor into an electric field and it will reach electrostatic equilibrium fairly quickly. The charges will move relatively fast. There will be a current that will flow across the conductor for a short period of time as those charges are rearranging themselves. But then once they cancel out the electric field, they'll stop moving. Now, if they tried to stop moving before the electric field was completely canceled out, then what would happen would be that there would be forces that would act on those charges to continue to force them to move until they reach electrostatic equilibrium. But once they're there, there's no field inside your conductor. So there's sort of four properties that we will use to define conductors that are in electrostatic equilibrium. The first one we've talked about is that the electric field is zero everywhere inside the conductor. It doesn't matter whether the conductor is solid or hollow. It simply matters that the conductor is a conductor. It has those free charges that can move around. Second thing is if you have an isolated conductor that's carrying charge, that charge is going to reside on its surface. So we worked a problem today where we talked about a non-conducting material, and we said that an insulator, you can smear that charge out over the entire insulator. But for a conductor, whether again a solid conductor won't actually have any charges, any of those free charges in the center of the conductor. They'll all move to the surface, and that's so they can cancel out the electric field on the inside. Third property is that if you get close enough, then basically, so it doesn't matter what shape you're dealing with, if you get close enough, effectively any shape when you're close enough to it appears flat. So this is sort of the same way that for us sitting on the surface of the surface of the earth seems flat, not distinctly round like it is. So if you get close enough to any conductor, basically it's going to seem like a flat surface, and what we'll see is that the electric field right near that surface will be perpendicular to the surface and will have a magnitude that's equal to, this will be the surface density charge over epsilon naught. So this is exactly the same thing that we're going to see from an infinitely large parallel plate. And so basically when you get close enough to your conductor, every point on the surface appears to be an infinitely large parallel plate and so it will all have a field that for very short distances acts like an infinitely large plate, has this value in terms of magnitude, and leaves the conductor perpendicularly. Lastly, if you do have an arbitrarily shaped conductor, the electric field is actually largest where the curvature is greatest. So when you have something that has something that points out, a conductor that has some shape that points out, that point will actually produce a larger value for the electric field than places that curve slowly. So things that have large curvature, that's where you're going to end up having more charges congregate to cancel out the electric field, and you'll end up with stronger values of the electric field at those points.